Thank you for coming. Welcome second time around at Yale. And you're right, this is going to be videotaped, but you shouldn't get your hopes up for breaking into show business because they can only see the back of your head. But you may have a very expressive back of your head, in which case somebody may notice you and give you a call. So this lecture on Einstein, generally the best way to clear a room other than shouting fire is to say something about Einstein, and then you have the place to yourself. So I'm very glad that you were not intimidated by the title, and my goal is called No Alum Left Behind. So everyone, you're all going to follow this, and when you leave this room, you will have a pretty good idea what it's all about. Okay. So maybe I should start by asking if you know how old the theory of relativity is. Any idea? Okay. I heard a century old. Turns out it is actually 300 years old. So even though Einstein was the father of relativity, there's a grandfather who is Galileo, and there's a godfather who is Newton. So they all came before and did a lot of things, and Einstein actually came much later. So that's what I want to tell you about, so you get a picture of where Einstein belongs. So the way we are going to do this is by the standard method for teaching the subject, which is to begin with two infinitely long trains. So I'm going to draw you a finite part of that train. So here is one train, and it's parked in Union Station in New Haven. This is train 1, this is train 2. So this is the top view of the train. Now, you get into this train, and all the blinds are drawn. You cannot look outside. Now, there's a reason for that. It's not because it's going through certain parts of New Jersey. It's because we're going to do a scientific experiment that requires you not to look outside. So here's, let's say you're on this train, there's another train. Before they shut the blinds, you can look out and see the other train. You can see it's also standing there. Then they close the blinds, and you settle down, and you explore the world around you. You can do whatever you want. Maybe you will pour yourself a cup of water, or you may be playing pool, or if you're a physicist, you will pull your mass and spring system from your pocket, and you will immediately attach it to the wall and pull this mass and see it vibrate. So we all have different ways of exploring the universe. This is what I do. Okay. Then you go to sleep, and when you're asleep, I tell you that I do one of two things. One is I leave the train alone the way it is. Other is that when you're asleep, I give it a speed of 100 miles per hour. And you wake up, and the question is, can you tell whether you have acquired the speed or not? That's the real question. You have to figure it out using the laws of physics. You cannot say, I know it's not moving because it says Amtrak. Okay? These arguments are sociological. They're not part of science. So the question is, will you know? And what Galileo noticed is that you cannot tell. You cannot tell in a moving train that it's moving as long as it's moving at a constant velocity. That's very important. If it's picking up speed and slowing down and so on, you will know. But if it's going at constant velocity, nothing will betray that motion to you. That's a principle we have all experienced. Once in a while, when the thing is very smooth or a plane is going very smoothly, you yourself realize that you're not aware of that motion. So the principle of relativity is a statement that you cannot tell when you're inside a train whether it's acquired a constant velocity or not. So where is the relative in all of this? I'm going to come to that. So if you open the blind now and you look at the other train, suppose you find the other train is going like that at 60 miles an hour. will you know whether you're the one who is in motion or the other train? Now, this has happened to us quite often when you're parked on a slope or you put your brakes and the car is in a slope. You see the other car going forward. You think you're slipping. You press the brake harder. You get the impression of movement. So the whole thing is, if you look out and you see this train going that way, can you tell? The answer is, you can tell there is motion between the two of you. That is a fact. But you cannot really say for sure you're the one who started off when you were sleeping, and maybe you did nothing and the other train got into motion in the opposite direction. So velocity between two such people is relative in the sense that we can perceive it, but we cannot be sure who is actually moving or whether there's any real sense in which one of us really is moving. In fact, if these two trains were in outer space, you just wouldn't know. Now, if you look at the other side, let's say, you open the window here and look, you see a lot of cows and trees. Cows are running at 60 miles an hour. Okay. Now the question is, what do you think is happening? Is it the cows or is it the train? So I know what you're going to say. You're going to say it's got to be the cows, but you realize theoretically Amtrak trains can move. So that's a possibility. You're not willing to admit that even though it's very remote. So you keep thinking it's the cows, but it could be. It could be possible that the cows are not moving, it's the train. So once again, there is no way to resolve the difference. So the summary of what was mentioned here is that constant velocity doesn't do anything that you can measure. If you're inside, you cannot figure out that's being given to you. But that's not true for non-uniform motion. That's not true for accelerated motion. For example, if the engine driver slams the brake, you're going to ram into the seat in front of you. Now, if the blinds fly open and you look at the other train, it'll be decelerating the opposite direction. Can you say, nothing is happening to me, you're the one who's accelerating the other way? Well, you cannot say that. First of all, you've lost all your teeth. You cannot say anything. But can you scribble a note and say, I'm not moving, you're moving? Well, he will say, if that's the case, how come you have no teeth? Because accelerated motion, namely the slamming of the brake, produces effects that you feel. You cannot pass the buck to the other person and say you're moving the opposite way. Or if you're an astronaut and your rocket is taking off, you're the one who feels all the G-forces. You cannot argue that the rest of the planet is going the opposite way because they seem to be doing fine. So here is the main thing. If you're inside a closed train and the train accelerates or decelerates or goes on a curve, you can tell. If it's going at constant velocity, you really cannot tell. That's it. That's what Galileo said. And that's called Galileo's principle of relativity, and it's more than 300 years old. So then the next person who comes in, not much later, is Newton. So what did Newton do? Well, Newton actually not only agreed with what Galileo said, he actually explained why it is true. So I'm going to tell you how, in Newton's point of view, you can actually understand what we all are aware of. Well, Newton, as you know, wrote down 3 laws of physics. I'm going to only talk about the first law. The second law says something is equal to something else. But I'm told in alumni reunions, I should not write any equations. that every equation costs the development office $600,000. So no equations. So I'll just take the first law. Okay? The first law is a rambling sentence, so it's quite safe. It says the following. It's the law of inertia. According to the law of inertia, if there are no forces acting on a body, it will either stay at rest, if it started at rest, or if it had an initial velocity, it'll keep maintaining the initial velocity, unless it's acted upon by a force. That's the first law. Basically, the first law says the velocity of an object will not change unless a force acts on it. Now, we are all familiar with the first law. I mean, here it is. I take this cup here, and I put it there. No force is acting on it. It stays where it is. So the law of inertia works for me. If it works for me, I'm called an inertial observer. Inertial observer is one for whom Newton's laws work. So this works. Now, The second part of the first law, that if something has a constant velocity, it'll keep on doing it forever, is hard to visualize. In daily life, you give a push to something, it goes a few feet and stops. It's hard to believe that it'll go on forever for free, but we know that if you reduce the friction more and more, or you went on ice and you give it a shove, it keeps moving for a long time before it stops. And an idealization is that if the ice is completely frictionless, whatever you set in motion will move forever. So that's harder to visualize in daily life, but Galileo had the imagination to realize that if you reduce the friction, that would happen. Nowadays, in outer space, you can easily verify that if you throw something, it'll just keep going at that speed without anybody pushing it. So that's the law of Newton, and I want to just show you the following. If Newton's law works for me, when I'm in the platform, let's say, this is the station, then it will continue to work even when the train is set into motion. In other words, if Newton's laws work before the train moved, it will continue to work even when the train has a constant speed. That's what I want to explain. That will show you that Newton's laws are valid in the moving train as they are on the static train. And when we say the world looks the same, what we really mean is the laws of mechanics looks the same. Because laws of mechanics tell you everything that you can see in the mechanical world is explained by them. So how do I know that the first law will work in the moving train? So that's what I want to explain to you. So let me draw a side picture of the train. Here is a train. There's a table here, which is frictionless, and there is a person sitting here. My drawing is a constant source of amusement for my class. So this is a person sitting on a chair, and this is a mug of beer which this inebriated person has put on a frictionless table. Now, the train is moving at 60 miles per hour. Now, I'm looking at the whole thing from the ground. So I see the whole thing going by. Everything on the train is going at 60 miles an hour. The beer, the person, everything. Now, what will the person in the train think? I argue as follows. The beer mug starts at 60 miles per hour. There are no forces on it because there's no friction, nothing. So it'll keep going at 60 miles an hour. The train, I've been assured, is going at a constant speed of 60. Therefore, the mug and the person are all going at the same speed, so the distance between them will not change. That's what I predict he will see, and indeed he will find the mug stays where it is. That's how I can show that the law of inertia will work on the train, because it works for me, and I can translate what I see into what he will see. Now imagine that the person gives the beer mug a shove, so it starts going away from him at a speed of 10 miles per hour. It starts out that way. What will happen next? I know what will happen next because I'm still on the ground. I'm allowed to use Newton's laws. And I say, this mug is going at 70 miles per hour. That's the 10 plus the 60 of the train. And this guy is still going at 60. So the difference in speed between them is 10, and that difference cannot change. That means, according to the person on the train, this mug will maintain its speed of 10. So I predict the person in the train will find the Newton's first law of inertia to be valid. Basically, the idea is the person in the train and I don't see everything the same way. We disagree on where anything is. I think the mug is going towards Boston. He thinks the mug is in front of him. I think the mug is going at 60 miles per hour. He thinks it's at rest. But the differences are only with respect to velocity, not with respect to acceleration. The fact that the mug's speed is not changing is true for me, and it's true for him. And that's all the first law of inertia says. Speed will not change without a good reason. Imagine now that suddenly the train picks up speed. So it starts going from 60 towards 70 miles per hour. What will the person in the train see? Well, I don't know if the person in the train is allowed to use Newton's laws or not, but I'm still allowed to do it because I haven't done anything. I'm still on the platform. So I argue as follows. This mug is still going at 60. This person is starting to move at 70. I know what will happen. The 70 will gain on the 60, and the two will soon meet. How will it look like in the train? The person in the train, it will look like the mug is sliding backwards towards him. That's what happens in a plane. During takeoff, if you leave something on the tray in front of you, it slides towards you, towards the back. In fact, everything in the plane that's not nailed down goes to the back of the plane during takeoff. That's why all the physicists sit at the last row collecting whatever stuff comes to the front. Okay. So, okay, if you have any question, you can ask me now. Any questions? Okay, so everything on the train will accelerate to the back of the train for no apparent reason. That means the world will not look Newtonian to the person in the train. That's how when he wakes up, he will know the train is accelerating. Because when you accelerate, nothing stays where it is. Things go back. You've got to be very careful when you use the law. You can say, I went to Grand Central Station, I left my iPod there, and I came back, it was gone. What about the law of inertia? Well, I guarantee you that the laws that were broken have nothing to do with Newton. So some unseen hand has come and taken the iPod. So that's always an explanation. But in an accelerating train, everything will accelerate backwards. That's the reason why accelerated motion can have effects you can detect. But uniform motion will leave no trace. You will never know. That's it. That's all there is right up to the time of Newton. So Galileo observed that. If you want, Newton explained that. He said, these are my laws of motion, and my laws of motion are such that if they work for me on the ground, they work for me on the train as long as the train is going at constant velocity. All right, so I have not said anything about one of the key ingredients in this theory, which has not entered the picture yet. You know what I have in mind? What do you think of, when you think of relativity, what's the first thing that comes to your mind? Right, okay. At least you think about the velocity of light. So velocity of light has not entered the picture, and now it's going to enter. So the velocity of light is something that has occupied minds for many years. Alfred E. Newman, who you might know, he said, this much I know about the velocity of light. It comes here too early in the morning. After that, every other quotation is going to be trivial. But I'll tell you what other people had to say. Galileo, for one, was very eager to find out if the velocity of light is finite or infinite. Namely, does it take any time at all for a light signal to go from here to there, or does it happen at once? So he did that by taking one of his friends, and he went on top of one mountain, and his friend went on top of another mountain. So this is Galileo, this is the friend, and they both had these lanterns, which can be covered. So here's the deal he made with his friend. He said, I will suddenly open my cover to my lantern, so it will emit a flash of light. The minute you see it, so the light signal is going to you, the minute you see it, you open the thing in your lantern. So I'll see that flash of light come here. So I'll look at how long it takes for a round trip. Then I'll divide the distance. I'll divide the distance by the time, and I'll get a speed. That was Galileo's plan. Now, we don't know what method he used to measure time. One theory is he used a water clock. Other was he used his pulse, which is a reasonably good way to measure, for example, the pendulum in the church where he was praying. Galileo noticed that the period of the pendulum doesn't depend on how big the oscillations are. That he did with his pulse. So I don't know how he measured it. So he got a speed, but you know that that was not the right speed, because what he was really measuring is just the time it takes to react. And how do you know that's what's happening? How do you tell that you're just measuring your reaction time? How will you know that's the case? Can you think of how to realize your own mistake?
Stand next to your friend.
Pardon me?
Stand next to your friend.
Or, yeah, that's right. That's very true. You can sit on the same mountain or go to a nearby mountain or a further away mountain. You keep getting the same time. You realize it's not the time of light travel you're measuring, but the delay to respond. So Galileo figured that it's very fast. He gave some multiple of the speed of sound, but he didn't say, I don't remember what it was. But he said it's at least that fast. The real breakthrough came in an astronomer called Romer found a way to find the velocity of light. That's a very ingenious method. So I'm going to give you a bare bone version of it. You can put bells and whistles on it, but the idea is still the same. So here is the sun. And let's say here is the Earth going on its orbit, and here is Jupiter going on its orbit. And this is Jupiter. And at the time when I want to do this thing, Jupiter is here, Earth is here. And there's a moon of Jupiter called Io, which is going round and round. Let's say it goes around exactly every hour. So every time the moon comes in front of Jupiter, I see it and I make a notation. I say I saw the Jupiter as a function of time. I draw a blip. Then 1 hour later, I should get a second blip, and at 2 hours, I should get a third blip, and so on, because all these motions are completely periodic. It's like a clock. But what you find is that the second blip doesn't arrive on time, but comes a little later. Third one comes even later, and the reason is that the Earth is moving away from Jupiter. So the delay keeps on accumulating till 6 months later. It's quite a bit, it's several minutes, compared to when the pulse is supposed to come. The 300th pulse, let us say, comes 10 minutes after it's supposed to come. That 10 minutes is then the extra time it takes light to go across the orbit of the Earth around the sun. And people have a pretty good idea. It's like 100 million miles. And then you take the extra time and you divide it and you get a speed. And he got a pretty good answer. The answer he got was like 200,000 kilometers per second. And the correct answer nowadays, we know, is like 300,000 kilometers per second. But it is a remarkable achievement. And you need something of cosmological proportions before you can find the velocity of light. You do anything in the laboratory, things happen so quickly. Later on, people found a way to measure it in the lab, but this is the first astronomical measurement. All right, so light was then shown to have a finite velocity of propagation, and the velocity was improved. And by the time I come to the next part of the story, people knew pretty much the answer is 300,000 kilometers per second. All right, so then there is a new development about light. People don't know what light is. They don't know what's going on. They just know it travels at this speed. Then a person called Young did an experiment which shows that light is actually a wave. Now, I should tell you what we mean by that statement. What does it mean to say something is a wave? Waves have one very important property. First of all, we all know what waves are. In water, you can have waves. The thing is going up and down in relation to some undisturbed level of water. Waves have the property that they can interfere, and that means the following. Imagine that this is your estate, and there is a beach here, and you park your yacht. I'm told to give this to the Yale alumni. Your yacht is parked here. I don't do this in the classroom because they don't know what I'm talking about, but you guys know. You all have one, right? Okay, so you put your yacht here, and the waves are coming. To block them, you put a barricade. So your yacht is very tranquil. Suddenly, there is a breach. And these waves will come from this opening now, radiate out, and they'll come to your boat, and the boat will shake. Suppose you want to avoid that. There are two solutions. One is to find a way to block this. But if all you have is, say, a sledgehammer, you can still make progress. Because you can go and you can make a second breach here. Now that looks like bad news because now stuff's going to come from here too. But you can arrange it so that when this guy and this guy meet, they cancel each other. Because you see, it takes a little longer to go from here to there compared to that one. So you got the crest and a trough and a crest and a trough. You can arrange it so that when a crest from here comes, a trough from there comes. So one is telling the water to go up, other is telling the water to go down, so it doesn't do anything. A little later, this one says go down and that one says go up and doesn't do anything. So you can find it, you can arrange it so that you don't have any activity here. That's called interference. So two waves can cancel. And if instead of water waves, if this was light and you had a source of light here and a dark screen with two holes in it, and you put another screen way behind to look at it, you will find patterns of dark and bright and dark and bright. Dark where the two cancel and bright where the two add up. That's called interference, and he showed that when you do it with light, you get interference. So it's a wave, but you don't know what it is that's waving. See, sound is a wave, but I know exactly what's moving. When I talk to you, when my diaphragm pushes in and out, it changes the air pressure, and the air pressure propagates to you, and it goes to your ear. Then the eardrum starts to move. And after that, I don't know, that's the biology department. Some wires come and pick it up, and stuff goes to your brain. Okay? So that's where we check out, at the eardrum. But I know that's how it travels, so that's the propagation of sound. In a violin string, also, when you pluck the string, we know the deviation from horizontal. That blip is what travels back and forth. For light, no one knew what it was. We know it's a wave, we know it's got a wavelength that we can measure, but what is it that's really shaking? And what's the medium in which all this is happening? That was not known. So Maxwell, this is this last character before Einstein, was studying electromagnetism. He was not interested in light, studying electricity and magnetism. So electricity is quite familiar, right? It's when you rub your feet on the carpet and you touch the doorknob, you get a spark. That's electricity. Magnetism has been known to people from ancient Greeks, when parents noticed that kids were sticking stuff on the refrigerator using some little black rocks. So from that time, magnetism has been studied, but we can say you have a magnetic field if the compass needle will do anything, then there's a magnetic field there. So what Maxwell was studying is how these electric and magnetic fields travel in space, and he found out they travel like waves, and he calculated the speed of the waves, and you put the numbers in, and you get a speed which is universally, oops. I will not write anything. I'll just write here 3 times 10 to the 8 meters per second. So he got that speed. Now, that was a real shock, that electromagnetic waves travel at exactly the speed as the speed of light. So they said electromagnetism must be light. Now, you've got to be very careful. Just because you're traveling, for example, if I'm running next to a buffalo at the same speed, doesn't mean I can conclude I'm a buffalo, right? We just have the same speed. So the fact that electromagnetic waves are the same speed as light doesn't mean it's light. Well, they said that's what it is, and they were right. But later on, we know that gravity waves also travel at the speed of light, but they are not light. But at that time, they were quite right. So light was, in fact, electromagnetic waves. And the question is, what are these waves moving in? They said, let's give it a name. We'll call it the ether. There's something called ether, and ether's everywhere. It's even between here and the distant stars. We know it's there because we can see the stars. If there is no ether between us and the stars, the light cannot travel without the medium. So ether's everywhere, okay? Then the speed of light is calculated to be this number, is always in the medium in which it travels. For example, the speed of sound is 700 and something miles per hour with respect to the air. If I travel now with respect to that air in the direction of the sound, the speed will change for me. The speed of sound will be reduced. In fact, you can eventually go even faster than sound. If you could fly in the Concorde, that's what it does. It goes even faster than sound. So the speed of sound is a number that's given with respect to the air in which it is traveling. So speed of light must be the speed with respect to the medium in which light is traveling, this mysterious ether. So if I go and measure the speed of sound today in my lab, I would generally not expect to get that number because in all probability, my lab is moving relative to this mysterious ether at some speed. That difference must show up in the speed of light. But when you measure it, you get exactly the answer as if you were at rest with respect to the medium. Then you say, okay, you know what? Maybe today my lab at this instant is at rest. But wait 12 hours or a few more hours, since the Earth is spinning, one instant you're moving like this, 12 hours later you're moving like that. You cannot be at rest the whole time. Also, you're going around the sun. You cannot be at rest the whole time. And yet, no matter when you measure the speed of light, you get the same answer. Daytime, nighttime, any time of the year, moving whichever way you like, you get the same answer. And one simple explanation was, maybe the Earth is carrying the ether with it. For example, the atmosphere we are breathing, we don't leave it behind as the Earth moves. We carry the atmosphere with us. Or when you go in a plane, if you talk to somebody across the other end of the plane, you don't have to worry about the fact the whole thing is moving because the air is being carried by the plane. You don't have to worry about it. So they said maybe that's what's happening. Maybe the ether is carried by the Earth. But one can show from celestial experiments looking at stars that you cannot take it with you. You cannot take the ether with you. Then you have a real problem. Here is this thing traveling in some mysterious medium. No matter who is looking at it, it has the same speed. You realize that's very strange. How can something have the same speed for everybody? Someone standing, someone moving the opposite way, they all get the same speed. So people didn't know what to make of it till Einstein came and said, I know what's going on. I know why light is behaving this way. Forget about ether. There is no medium called ether. We don't need it. I'm just going to postulate that the speed of light is same for everybody, no matter how they are moving. Now, you might think, this guy is famous for saying that. I mean, he doesn't explain anything. He just says it's the way it is because it's the way it is. I'm going to postulate it. So if that's all he had done, it would not be the whole story. He explained why the speed of light is the way it is. He said, if I go to this train that Galileo talked about, and I wake up, I do all experiments with water and masses and springs, and they all look exactly the same as before. But suppose I sent a light pulse and measured its speed. If the speed of light depended on the speed of the train, I will get a different answer when I wake up. And from that difference, I can deduce the fact that I'm moving. That means the laws of mechanics conspire to hide my motion, but not the laws of light, laws of optics. He said, I don't buy that. I don't believe that some laws of nature remain the same in a moving train and other laws vary. So the speed of light behaves the way it does because it's part of a big conspiracy to hide your velocity as long as it's uniform. That's why light behaves the way it does. It had to. If it had behaved any other way, a person on a moving train can detect her speed without looking outside. That means there's at least one thing that is different in a moving train. Maybe mechanics is the same, but optics is different. He said, I don't buy that. Everything has got to be the same. It was an act of faith, really. Even though he's not a very religious person, most scientists may be religious, may not be religious, but physicists certainly have a belief in the order of natural phenomena. We believe we are playing against a reasonable opponent, that the puzzles have reasonable and clever answers. And whoever designed the system certainly will make sure that the laws of science behave uniformly, that everything is same on the train, not just mechanics, not the first 10 chapters of my book, but the whole book. So he said that. Now you can say, is that all he did? No, because in saying the speed of light is a constant, he then set himself up for a lot of consequences, which are very bizarre. And that's what I'm going to talk about now. Because you should think about what it means to say the speed of something is a constant. So imagine you're standing on the ground, and there's a car, and it's speeding by at some 60 mph. You clock it as going at 60. Now, suppose you get into another car, and you travel in the same direction at 40 mph. You expect the speed of this to be 20. Everybody agrees. You've got to subtract your 40 from that 60. That's how velocities add. If you had a velocity of 60 from the ground, and you go at 40 to the right, you subtract your 40 and you get 20. But what I'm telling you is, if this had not been a car but a light pulse, signal of light is traveling, if it had a speed c on the ground, it has the same speed c when seen by a moving car, moving in the same direction. In fact, even if this car is going at half the speed of light, it will still appear to travel at the full speed to that person. That is what Einstein says is happening, but you realize that means big trouble, right? It's not the way things behave. So let me make it very, very clear. Here's a light signal going at speed c as seen by the ground. I'm going at a speed 3/4 of c. What does he think I should get? He thinks I should get 1/4 c as the measured speed, but I get c. So that the velocity I get is much bigger than what he expects. So how do you explain that? So you say, look, I thought you will get 1/4 of c, but you're getting c. So something's wrong with the way you're doing your measurement. How do you measure its speed? You see how far it goes by putting some meter sticks, one against each other. Then you see how long it takes with your clock. You divide distance over time. And in that calculation, somehow you're getting 4 times the answer. Now, there are 2 ways in which it can happen. One way is that your clocks are not running at the same rate as before, when we were both standing relative to each other at rest. The minute you went on this train, some of your clocks have slowed down. Suppose they're running at 1/4 the normal speed. That means when light has gone for 4 seconds, you think it's gone for only 1 second. So you divide by 1 instead of 4. That's why you got this 4 times the answer. Another option is the meter sticks, which we bought from the same store, which you used to agree before you got on your train. Your meter sticks have shrunk. They've shrunk to 1/4 their size, so that when light has gone only 4 yards, you think it's gone 16 yards. So you either inflate the numerator or reduce the denominator in the velocity calculation to get this, or maybe you're doing both. Maybe both things are happening. But something has to happen. So you have to abandon your notion that meter sticks and clocks run at the same rate in a moving train as in a static train. And then he went on and calculated the amount by which these two things happen. That's a calculation I won't perform, but I do want to tell you some of the interesting consequences. Then I will stop talking, then we can explore the consequences. The first consequence is that events which are simultaneous for me may not be simultaneous for you. So here's an example you can give. So imagine a pair of twins, okay? One is born in LA, one is born in New York. Did you listen to what I said? This is what I said. So when I mentioned this to my class, they pointed out that no ordinary mother could have given. This is the mother from the Yo Mama jokes. She's so big she can give birth to kids coast to coast. All right. So anyway, let's forget the kids. Let's say there is some other event that takes place simultaneously according to me. Then the claim is that if you go on a rocket ship or any other state of motion, you will think they're not simultaneous. That is really interesting, right? Because we have a notion that when two things happen at the same time, say in LA and New York, that's the real meaning in which they happen at the same time. We're not fooled by the fact the time difference of 3 hours. We know there is a sense in which they really did happen at the same time. We think that's an absolute statement. But the point is that if the whole events are seen by a moving observer, they will not be at the same time. And this is how Einstein explained it. So he said, let me take this train, which is at rest, and I want to make two things happen at the two ends of the train at the same time, maybe 2 explosions. So what I'm going to do is I'm going to take 2 mirrors placed like that at some angle. I'm going to send a light signal from here. It'll split. One will go to the left, and one will go to the right. And since I'm right in the middle of the train, they will go and hit the 2 ends, and let's say they trigger 2 explosions. Those explosions happen at the same time. I couldn't have done it more carefully. But now imagine that the train that I am in is actually moving relative to the platform, and you are seeing it from the platform. To you, this is what's happening. Let's see what you will say is happening. The light signal left here, this signal is going to the right at the speed c. The speed of light is the same, but this end of the train is moving away from that signal, whereas this end of the train is rushing to meet the signal. It's very clear this end will hit first, and a little later, the light will hit that end. So you will agree that to the person on the ground, the 2 events will not be simultaneous. Now, here is where people sometimes ask, why do you use this light signal? Why not send 2 pigeons, release 2 pigeons and see what they do? Or just shout, hey, do that, and the 2 guys at the 2 ends of the train do what you said. The reason you don't do any of those is we don't know anything about the behavior of sound in this new relativistic physics. We don't know about, you can send 2 Federal Express guys. Will they get that at the same time? We don't know, because we don't know how they behave. But one thing we do know is by postulate, the velocity of light is a constant, regardless of the source, regardless of the observer. That's why I can say with confidence that even though the signal is emitted in the train, the right signal and left signal both travel at the same speed, c, one towards the end that's running away from it, one towards the end that's rushing to meet it. Consequently, they won't be simultaneous. Now, it turns out that this lack of simultaneity is really there, and you just cannot say who is right and who is wrong. You just can say, I made it as simultaneous as I could to the best of my ability. But you don't have to agree. It's a very interesting case where people really can disagree on what is simultaneous and what's not. It depends on the observer. So that's the immediate consequence. You can see where it came from. You got to do more work if you want to know how much is the time difference. For that, you got to do calculation. But the fact that they won't occur at the same time, you can see immediately. Now, this also means that two events which are simultaneous for one person can occur in different sequences. Event A can occur before B, and I can find a guy for whom B occurred before A. Now, if you're Einstein, you should again get worried. In fact, the greatest thing about Einstein, which you admire once you start practicing any kind of science, is not only that he was very clever, but he was very gutsy. Because once you invent something new, and the mathematics takes you in all kinds of directions, you have no choice. You're wedded to that formalism, and you got to defend all the consequences of your theory. So here's the consequence. A and B are two events which are simultaneous for me, but not simultaneous for you. You can also show that if A occurred after B for me, then B can occur after A for someone else. That can lead to a lot of paradoxes. So event A is my father is born. Event B is I am born. Okay? Now there's another observer for whom I am born, but my father is not born yet. You realize that poses a lot of problems, right? The nurse says, what shall we name this kid? I don't know, his father is not born yet. No, you don't want that to happen. So there are certain events where one event is causally connected to a second event, where A is the cause of B. In this case, my father is the reason I'm here. The theory should not allow the order of those events to be exchanged. There are other events where A could not have been the cause of B. That's defined in relativity as such that there is no time for a light signal to go from event A to event B. Then no way A can influence B. In that case, you can find another person for whom the order is reversed. So the order of events is not, in some sense, is absolute. If A is the cause of B or could have been the cause of B, theory doesn't allow you to exchange that order. But if they are not causally connected, you can find people who completely disagree on when something happened. Okay, so that's the second thing involving time. And here's another thing involving time that's very interesting. Remember I said maybe a moving clock slows down? Let's see how that can happen. Now, if you take the clock that I'm wearing, there's no way we can show that because I have no idea what's in it. You open it, nothing is moving nowadays. We don't know how clocks work. And Einstein didn't know how clocks work either. But he devised, or at least to teach it, we devised a very simple clock where we can all understand why a moving clock slows down. This clock is simplicity itself. You got two mirrors, and you have a source of light that emits a blip. It goes to the top mirror and bounces back and goes back and forth. And every time it makes a round trip, it hits a detector and it goes click. Okay? That's my clock. The round trip is L plus another L. You divide by speed of light, you get the time. That's the time period of my clock. So I have a clock like that, and you have a clock like that, and your clock and mine are identical. We bought them at the same store. But now you go on your train, you hold your clock, and I look at your clock. Here is what I find. Your clock is doing this because you are moving according to me. So when the light was emitted at the bottom, you were here. A little later, you were there when it hit the top. Then you were here, and then you were there. In other words, an up and down motion in the train looks like a zigzag motion from the ground. We can all understand that. But a zigzag path, we all know, is longer than straight up and down. And it's a very simple calculation to see how much longer, and that just involves Pythagoras' theorem, namely comparing the hypotenuse to the vertical side, and you can get the time difference. So I can tell you how much you will be slow. But here is the paradox. Paradox is you are entitled to say you're not moving at all because the laws of mechanics are everything is same for you as for me. In fact, according to you, my clock is going that way, zigzag the opposite way. So you understand how if you and I have two clocks, my clock is up and down, yours is zigzag for me, and according to you, the picture is just reversed. So each person is able to argue the other person's clock is running slow because it's not taking the shortest path. It's going on a zigzag. But this leads to a paradox. What if these two guys meet? When they meet one day, whose clock will really be behind? Because each seems to have a solid case. So that is the twin paradox. The twin paradox is the following. You have these same twins. One is now in Houston or in Florida. The other gets into a rocket, goes on an orbit around the Earth 500 times, and they come back. Now, the person on the ground says, hey, you've been moving, and therefore your clock is slow. Therefore, when I compare your clock to my clock, your clock should have ticked fewer seconds than me. But what if the person in the rocket says the same thing? He can say, I'm not moving, you're moving, so you should be. In fact, forget clocks. The human body is a clock. I am a clock. If you watch me patiently, in a few years, the rest of my hair will fall down, my teeth will fall down. You can measure time in decades by watching human beings. If you cannot wait, you can watch the cells, how they grow and die and they replicate. So the human body is a clock. Therefore, the human body's aging should also slow down in a moving plane. So the twin paradox is more dramatically illustrated by saying the following. Suppose the twin on the Earth waited 10 years for the journey to end. And the twin on the rocket, by that time, is aged only 5 years. So when they meet, the rocket twin should be younger than the one who didn't go on the trip. But what if the rocket twin says, I never went anywhere, you went somewhere, you should be younger? The question is, when they meet, who will be right? You have to answer that. If you're Einstein, you have to provide a definite answer, because when you do the experiment, you can get only one answer. So the answer that Einstein gave is that the person who went on the rocket will be younger. Now, why is that? Why is it that they both cannot make the same claim? The answer is that I am on the Earth, I never went anywhere, Newton's laws are valid for me the whole time. You got into this rocket when, for a brief period, you were accelerating. You knew that. Newton's laws didn't work in your frame. If you accelerated too much, you were going to die, not me. Then you accelerated, picked up speed, then you can go at uniform speed. Then you slowed down, turned around, picked up speed, and came back, slowed down, and stopped. So you have done a lot of acceleration. Therefore, you are the person who cannot ever claim to be equal to me. So the answer to the twin paradox is not really a paradox. The twins are not equal in their claim. One had accelerated motion, and the other didn't. So these two clocks, which are going in opposite direction, can never be compared unless one of them stops moving and goes to the other one. Whoever stops and turns around and goes back, that clock is moved. That clock will be behind the other clock. So this is the manner in which the twin paradox was resolved. And people now find that even though human beings cannot be kept alive much longer by traveling, elementary particles can be. A lot of particles produced in Geneva, for example, they're not supposed to live very long, but if they go at very high velocities, their internal clock slows down and they live much, much longer than you expect. So that is the behavior of time in this theory. The behavior of length is more complicated, so I don't want to explain that. But the claim is that whenever a rod starts moving relative to you, you will think it's shorter than it is. Everything that's moving will appear short to you. And according to that person, everything you have will appear short to that person. You've got to make sure there are no paradoxes there. These are other things one can study if one wants to. But I didn't want to do all of that. So let me just say, the point I want you to carry is that I'm going to stop so you have at least 10 minutes to question me. The point was, the principle of relativity says that when you get into a train, which is going at a constant speed, there is nothing that will betray that constant speed to you. It makes no difference. It was true for mechanics, and in the end, it's also true for light. But if it's true for light, it led to a very strange requirement that the speed of light be the same for all observers. And that is very contradictory to popular intuition, where the speed of something depends on how fast you're moving. So Einstein said, well, I will not let light change its speed. I will let our measurement of time and space change suitably to accommodate the constant velocity of light. That's what led to the change in the notion of simultaneity, how long it takes for a clock to tick, how long is any object. It all depends on how you measure it. So space and time got revolutionized so that in the end, the speed of light comes out to be the same. That's the first part of relativity. E equal to mc squared is not anywhere near this. In fact, it's not a central result in this theory. It is a great phenomenological consequence, but you can see there is no reference to that right now. And it's not that easy to explain as what I was able to explain to you. So it's really a footnote, were it not for the great consequences it has as a logical structure that comes somewhere else. What I mentioned to you is the heart of the special theory. A few years after that, Einstein generalized his theory to the general theory of relativity, in which he said, I don't even like the fact that an accelerated person has to admit he's accelerating. I want him to also talk his way out of acceleration. You can say, how can that be? When you're in an accelerated train, all kinds of stuff starts rushing to the back of your train. How can you talk your way out of it? And here is how you can do that. Here is my train. And if I'm accelerating, you agree anything that's not nailed down goes to the back of the train, falls at a certain rate to the back of the train. Here's what I can say is happening. My train is not moving at all. But when I was sleeping, you went and put a huge fat planet behind my train, which is pulling everything I leave here towards that. So you cannot tell if you're in the gravitational field of a planet or whether you're accelerating the opposite way. So that's how gravity enters the theory. So Einstein's general theory is really a theory of gravitation. See, gravity has the remarkable fact that everything falls at the same rate. That's a remarkable property of gravitation. Whatever you drop falls at the same rate. Therefore, you can imagine being in outer space, no gravity, but your lab is accelerating upwards at 9.8 meters per second. There also, everything you drop will go to the floor at 9.8. Basically, the objects are not going, the floor is rushing to meet them, but you cannot tell the difference. So that's how the gravitational theory was deduced by Einstein a few years later. That is viewed by one and all as the most imaginative leap made by pure thought, because that was done not because of any experiment, but by sense of dissatisfaction with the special theory, that it made people in uniform motion equal, but he wanted to make everybody equal. And then in the quest for that, he found this great theory. All right, so I will stop now and answer questions. Thank you. Okay, I see a hand in the back. Yes.
Okay, so in the beginning when we did the training sample, so if I ice table that friction table, if I push the mug at 10 miles an hour and then the train accelerates at 10 miles an hour, will the mug stop?
Remember, 10 miles an hour is the speed. You give it a speed of 10 miles an hour, and if you are going, that means from the ground, the beer will be going at 70, you'll be going at 60. If you pick up speed, that's acceleration. If you go from 60 to 70, if you gain speed, then you know you will catch up with the mug. But from the train point of view, it'll look like the mug came back to meet you. Okay. Yes?
Doesn't the general theory bring back the paradox?
In the general theory, there is no paradox at all. So you can also solve it. But in other words, you can say, this involves accelerated motion, so we won't answer it. So if you want, you can use the general theory to actually show very clearly why one person will be slower than the other one. Yes?
In the example with the explosions at both ends of a train,
Yeah.
if you move the mirror closer to the front of the train, would that make it appear that the explosions are simultaneous to an observer on the ground?
Yes. But it won't be simultaneous for a guy on the train. Yes, you can arrange it so that the person on the ground is satisfied that they are simultaneous, but you won't be in the train. So if you do it so it's simultaneous for you, it will not be simultaneous on the ground. But you're quite right. You can move the mirror closer to the other end, front end of the train, so it's simultaneous for the person on the ground. But then it's not simultaneous for you. So it is still true that you could not agree on what's simultaneous. Yes?
In the example about the different velocities between the 60 and the 40-mile train,
Yeah.
and if you go c and 3/4 c, the difference is not 1/4 c. If the two trains are moving at 1/2 c and 1/4 c, then is the difference in the velocity 1/4?
You got to be careful. The only speed that is same for everybody is the speed of light, okay? A train going at 1/4 the speed of light will not appear to have that speed for everybody. Some people can say it's less than 1/4, some people can say it's more than 1/4. So it's not that any formula that has a c in it doesn't change. It's got to be really at speed of c. So the velocity of light is the only speed that is same for all people. Half the velocity of light is not the same for all people. Oh, one here and then one there. Yes?
You
Yes. Well, a gravity wave is. So maybe one way to think about gravity waves is that we are supposed to be in a space-time in which there is something called a curvature of space-time, so that the distance between points can be stretched or contracted. It's like saying maybe you're on a rubber sheet and you mark some dots, okay? And the dots are spaced uniformly. Suppose a ripple goes past that rubber sheet. You realize that when the ripple goes past you, some points will move further away and some will be closer. So that's a real wave on a real diaphragm producing the distance. Now it turns out in free space, if you take 2 points, which you think are a meter apart, when a gravity wave goes past, it's a change in the underlying fabric of space-time, so that for that short time, they will seem to be either closer or further. So gravity waves, one in which the actual distance between points changes when the wave goes past.
So if you have a positive and a negative charge and you put them together, that generates light, doesn't it? So would that create light when the gravity wave comes?
Yeah, if they accelerate, it'll also emit light. That's correct. Yes.
Okay, so you said before that the reason the clocks would be different with the spaceship example is because of Newton said it's because of the acceleration and the deceleration of the rocket rather than, and that didn't happen on the Earth, and that's why the 2 times would be different. So let's say you accelerate the rocket to like its orbit, and you orbit 10 times around the Earth and then decelerate and come back, versus the example where you accelerate to the orbit 500 times around, and then come back. If the velocity doesn't affect the time, then would those 2 clocks read the same, have the same difference?
Your question is, it's only the accelerated portion that you think will make a difference? Is that what you're saying? Mm-hmm. No, it will actually also remember how long you went on a straight line also. Yes?
How do you handle the Doppler effect?
Well, so the Doppler effect is the phenomenon that when waves are emitted towards you, so a crest comes and a trough comes and a crest comes, you time them, that's the frequency of sound. But if as I talk to you, I also walk towards you, which I can do after some practice, then you will find out that the crests appear to come to you a lot quicker, because I emit a crest, then I move and emit the next one, so they're squashed. That's the Doppler shift. And that has nothing to do with relativity. We can understand that in Newtonian mechanics. But in relativistic mechanics, that's the added fact that when I'm moving, my clock is different from your clock. And that's called the transverse Doppler effect. And one way to see that, that's an extra contribution to Doppler effect, but you can best see it when you're going around another person. When you go around another person, you're not emitting waves towards him or away from him, and yet there will be a shift. That's because when you're moving in a circle, your clocks are different from mine, and your frequency will be different from mine. So you think you're singing at some frequency, I will hear it at a different frequency.
That's all right, but with light as a constant,
Yeah.
the emitter is moving toward you. Do you get it? We talk about the red shift.
Yeah.
The expanding
Right.
universe. That's the paradox I've never quite grasped.
Yeah, that shift is really, that really can be understood as a classical Newtonian shift. If a galaxy is receding from you, the light it emits is shifted towards the red because the crests are further apart than they normally would be. So the color looks redder than the actual color. Yep.
Is warp speed possible?
Okay. First, I got to tell you, I don't know what a warp is, okay, because we don't know.
Warp 1 is speed of light.
Okay, warp 1 is speed of light. Okay, speed of light, as far as I understand, definitely not possible for any material object. The only thing that travels at speed of light is light. That's what Roosevelt said. The only thing traveling at the speed of light is light itself. Okay, nothing. No. Pardon me? Here's a question. If you can go faster than light, a lot of things will happen. One of them will be that you will see the effect appear before the cause. And that will lead to logical contradiction. That's one of the consequences. So that you will find that if I fire a bullet, can you move away a little bit? Yes, thank you. And it hits that door, okay, it hits him. then this is the cause, that's the effect. You will find another observer, if you go faster than light, that he got shot, and I've not even pulled out my gun. Meanwhile, somebody grabs my gun. This poor guy's been shot for no reason. Okay, he's on a risky mission here, right? Okay. Any other things? Oh, yes.
If you're on a train that's going at the speed of light and then you turn on a flashlight, where would the light be? Would it fill
Yeah.
up the whole room or would it just stay in one place?
Okay, now you cannot go at the speed of light, but imagine you're going at 0.99999 times the speed of light. Everything will be the same. The minute you turn on the light bulb, the light will spread out and illuminate the room as if you were not moving. You will not know. In fact, here's the point. You somehow say, I'm going at that speed, right? With respect to whom? How do you know you're going at the speed? Because it's always relative to somebody else you're going at that speed. Normally, you may mean with respect to Mother Earth, but that is an arbitrary human interest, right? Normally, the speed of some system is defined only relative to other systems. And the claim is that you cannot deduce any intrinsic effects due to that speed. So you won't know. As long as it's less than the speed of light, everything will look exactly the same. But when you make a long trip, and here's another thing. How far can we explore our universe? Suppose a star is 200 light years away. That means even if you travel at the speed of light, it's going to take you 200 years to go and 200 years to come back and brag about it, right? Can you do it if your lifetime is only 100 years? The answer is you can. Because if you go fast enough, you stop aging. You can go to the planet, you can turn around and come back, and you could have aged only 2 days. But you won't have anybody to brag to because everybody is gone. They're 400 years old. Okay. But you can do it. So there is no limit. It's very interesting. The speed of light imposes a limit on how fast we can travel. So it looks like in 100 years you can go only 100 light years, and that's wrong. Because as you travel, you slow down your clock, your own biological clock. So that's the other thing. If you're worried about a biological clock, and you're waiting for Mr. Right or Mr. Right now, Mrs. Right, whatever it is, get on a rocket ship, okay? And tell them to call you when somebody reasonable comes along.